Right then guys, so we're looking at mass spectrometry today, which is a nice follow-on from the electron gun equation, and a nice follow-on from the magnetic fields we were looking at, because you can see how that theory is used in practice for particle accelerators. So, point of a mass spectrometer is, as the name might suggest, to find out the mass of things. We're not talking large things, we're going to use mass balances for that. We're talking not quite subatomic, but molecules, atoms, things that sit in the middle between wanting to use a mass balance and just having to use fundamental mathematics to find out the mass. So, first thing we need to do is to take whatever it is we want to find the mass of and vaporise it. That's normally done one of two ways. We either use a rapid heating laser to cause it to vaporise, become a gas, or we use like a heating coil, similar to the electron gun equation, to boil off the outer atoms. It gets hot enough. Depends on what the substance is. That's what we do. So, we've vaporised it, which turns it into a gas. The gas of the material is ejected into the ion chamber. Now this is where we use the electron gun to bombard that gas with electrons. Some of them are going to knock off electrons of the gas, and so you're going to end up with a gas of your element with a positive charge in this ion chamber. Once it's got a positive charge, you're going to use an electric field to accelerate it towards the velocity selector. Now the velocity selector is really, really elegant, really beautiful part of physics, giving us a really simple result. What we want is a dead straight line of our gas, a dead straight line of our gas particles, so that they arrive here in a straight line. But what's more importantly, we need to know their velocity. Because later on we're going to think about momentum and radius of path to figure out their mass, but to begin with we need to know velocity. In the velocity selector we have an electric field. We remember the equation for that was Fe is EQ, so the force due to the electric field is electric field times charge, and we've got the force due to the magnetic field, which is BQB. In the velocity sector they set up an electric and a magnetic field at 90 degrees to each other, so that the particle wanting to change direction because the magnetic field is balanced by it wanting to change direction by the electric field. And that ends up with us having EQ equals BQV. First thing you'll notice, our Q's cancel out. So we're left with E equals BV. Really convenient our Q's cancel, because here in the ion chamber there's no way of telling if it's singularly ionised, doubly ionised, triply ionised. So charge needs to not matter at this section. It doesn't matter because they're cancelled out. One last rearrangement and we can see that the velocity is equal to E, the electric field, divided by B, the magnetic field. And so we pick the electric field, we pick the magnetic field, we designed them, we decide their strength. So because of that, we can select for certain velocities. If it's going faster, it's going to spiral one way. If it's going slower, it's going to spiral the other way. So only gases passing at that velocity will pass in a dead straight line, and if we have this gap here practically zero, only gases with that velocity in a straight line are able to pass into this chamber. So, we've charged our gas, we've given it its velocity. Next thing we do is inject it into an area where there's a magnetic field. In this case it will be going into the board. We've got charged particles in the magnetic field, they're already moving in a straight line, we're going to have circular motion. Circular motion, F equals mv squared over r. There's going to be a magnetic force, F equals BQB. travelling in a circular path, they are going to be equal to each other. So we've got mv squared over r equals bqv. First thing we're going to do, cancel our v's out. Next thing we want to do is rearrange this for r. So that's going to end up giving us r equals bq over mv. Beautiful, simple, logic, makes sense equation. If there's a bigger magnetic field, or you've got a bigger charge, it's going to curve more. It's going to be more affected by the magnetic field. If it's heavier, if it's faster, I meant to say curve less. It's going to curve less here, we're going to have a tighter circle. If it's heavier or faster, we're going to have a wider radius. It's travelling faster, it's harder to turn. Think about a car. The slower you travel, the smaller your circle of turning. The faster you go, the bigger your circle of turning. It's exactly the same principle on the molecular level. So now we're in a position where our atoms, our charged molecules, are going to strike a photoconducting cell, so we can tell where they've hitten. So we can simply measure the radius of their curvature. So we know radius, we know B because we've created the magnetic field, we know velocity because we've figured out the velocity, we've set the velocity. On the surface we don't know Q. What we can do is say, well, this one here must be charged 1, the next place it hits must be charged 2, the next place it hits must be charged 3, so on, so on, so except the other way around. The singularly charged one would have the biggest radius, doubly charged have a slightly smaller radius. So we can look at the position of where they're hit and figure out what their charge is. So we know everything, we can figure them out. We can measure R very, very accurately. We can measure B, Q and V very accurately. We can end up knowing the masses to 6 or 7 or 8 significant figures here. This is a tremendously accurate way of figuring out the mass of objects. What I'd like you to do now is if you can have a look at page 139 in your textbook, I'd like you to attempt the summary question 3. So pause me, try that now please. Hello, we'll come back. So, looks like a complicated setup, there's a lot going on there. All you need to do is calmly apply the equations we've looked at. So we know that R equals mv over bq. We know that the velocity is E over B. We could substitute E over B into R, but I'm just going to do this one step at a time just to make it a bit clearer, make it easier to spot if we've made any mistakes. So the electric field is 600 volts per metre. The magnetic field, 45 millitesla, so that's times 10 to the minus 3. So that's going to give us a velocity of 1.3 times 10 to the 4 metres per second. A bit slower than the electrons we were looking at last time. This is a molecule, an atom of iron. So an electron's got a mass of to the minus 31. Here we've got a mass of to the minus 25. We're talking 6 orders of magnitude bigger. It's going to have a smaller velocity. So now we know our velocity, we can look at using this equation. I'm only going to do one isotope for you. So if we look at isotope 54, we're given the mass of the proton. It's 1.66 times 10 to the 27th minus 27. We can figure out the mass. We've just found out the velocity. 1.3 times 10 to the 4. We're not given 2 magnetic fields, so we're going to have to assume that the magnetic field where the particle is, my diagram's gone now, where the particle is doing that, is the same magnetic field as they use in the velocity selector. So our B is still going to be 4.5 times 10 to the minus 3. And it mentions early on, it doesn't give you a number, but it says it's a singularly ionised isotope. Means it's got a charge of, if you're a chemist, 1. If you're a physicist and you know what you're talking about, a charge of 1.6 times 10 to the minus 19. You think you can plug all that into your equation, into your calculator, push equals, don't. You will make a mistake. One step at a time. So our top, 54 times 1.66 times 10 to the minus 27, becomes 8.9 times 10 to the minus 26. Next step, let's do the top row. The top row becomes 1.4. Hang on. You know we say one step at a time. Let's see if I've made a mistake. My notes here will tell you why I think this is wrong. I've got wrote down in my notes that it's 1.4 times 10 to the minus 29. What's wrong with that? I had a 26, I've multiplied it by 4, and the power's got smaller. Yeah, I've wrote 29 on my notes, I should have wrote 21. One step at a time. I make mistakes, and I'm pretty good at physics. You're going to make mistakes as well. One step at a time, and you can notice them. So 1.4 times 10 to the minus 21. Let's do the bottom. That gives me 7.2 times 10 to the minus 21, and gives me a much nicer answer than the nanometer I got in my working. 1.4 divided by 7.2. So 19 centimetres. Two things are important here. You need to be able to describe how a mass spectrometer works. I suggest you re-listen to the start and try and turn it into 4 or 5 bullet points. Second thing we need to be able to do is apply circular motion and magnetic force to this situation. The R equals mv over bq, you'll never be given that equation. You'll have to figure it out yourself for the situation. Okay, so read through the pages in the textbook about this. Try and do the isotope 56 and 57, and I'll see you Tuesday, guys. Thank you.